Alright, so this is a review of Le Chatelier's principle. We're going to go through a sample problem. This is useful review for the regular grade 12 chemistry as well as the AP chemistry class. So we see here a balanced equation in front of us, and the first thing I notice is that it's a homogeneous equilibrium. Everything here is in the gas phase. You have carbon monoxide reacting with hydrogen gases, and it's producing methanol vapor. When everything is in the same phase, whether it's gases or aqueous, for example, then this is called a homogeneous equilibrium. We notice that delta H is indicated. Delta H is called the heat of reaction. It can also be called the enthalpy change. And I notice right away that it's a negative sign here, negative 56.1 kilojoules per mole. When we see that delta H is negative, it tells us that the reaction that we have written there is an exothermic reaction. So the forward reaction here is exothermic because the delta H is negative. Now some people would actually take that information and use it to write the word plus heat on the product side of the equation, because when this reaction goes in the forward direction, it produces heat, being exothermic. So if you held this in your hand, say in a flask or in a test tube, that the container would feel hot as the reaction shifts forwards because it's producing heat. So we're told here that we have the system in a closed vessel with all three substances present at equilibrium. And we're asked to explain what happens to the mass of carbon monoxide when we perform various stresses. Now I look over at the equation and I see carbon monoxide is on the left-hand side of this equation. So when this reaction shifts in the forward direction, as we normally think of a chemical reaction, then we know that the things on the left are referred to as reactants, and they get used up. So when this reaction shifts forwards or to the right, carbon monoxide will be used up. It's one of the reactants in the forward reaction. On the other hand, if it were to shift in the reverse reaction, then carbon monoxide would actually become a product. In the reverse reaction, things on the left are being produced. So in that situation, carbon monoxide would be produced, would be increasing in mass. So when we shift forward, there will be less carbon monoxide. When we shift backwards here, there will be more carbon monoxide. So now let's look at this first stress. We're told what will happen to the mass of carbon monoxide if we add some hydrogen gas to the vessel. Now, I can explain this with kinetics, or I can explain with the reaction quotient. On a test, you would choose one method or the other. You wouldn't waste time explaining with both methods. So first of all, with kinetics, we know from our kinetics unit that one of the factors that affects rates is the concentration of reactants. So I notice here that in the equation, hydrogen is a reactant in the forward reaction. So H2 is a reactant in the forward reaction. Now why is that important? When you add more hydrogen to the vessel, we increase the concentration of hydrogen because we've added some more hydrogen. This will increase the rate of the forward reaction, where hydrogen was a reactant. The reverse rate is unaffected, okay, because hydrogen is not a reactant there, so unaffected. So now what do we have? We have a faster forward rate and a reverse rate that didn't change. So if you think about that for a moment, if the forward rate increased and the reverse rate doesn't change, then the reaction will shift in the forward direction. So we get a forward shift. And as we said a moment ago, if the reaction were to shift forward, we'd end up with a lower amount of carbon monoxide, so the mass of carbon monoxide will decrease. Okay? Now let's try to explain that using the reaction quotient. If you're going to explain with the reaction quotient, you must write the expression for Q. I'm going to write it up here, and we're going to refer to it multiple times. So the reaction quotient Q is the same expression as the equilibrium expression. So I'm going to write the concentration of methanol, CH3OH, raised to the power of 1, because its coefficient is a 1, divided by the concentration of carbon monoxide, and divided by the concentration of hydrogen squared. You remember when you're writing an equilibrium expression, you leave out solids and you leave out liquids because their concentrations are constant during a reaction. You only include gases and aqueous species. So now, we're adding hydrogen to the vessel. So let me just indicate that here as my first statement. So concentration of hydrogen increases. Now looking at Q, we see that hydrogen is in the denominator of Q, and we're thinking of this now just as a fraction. If you were to increase the concentration of hydrogen, you're increasing the denominator of your fraction. When you have a larger denominator in a fraction, the fraction gets smaller. So since hydrogen is in the denominator, Q will decrease. Now when you start in this problem, we were told that we were at equilibrium. Since we were at equilibrium initially, Q, the reaction quotient, would have been equal to Kc, the equilibrium constant. But now Q has decreased. So if Q is decreased, Q is now going to be smaller than Kc. Kc, of course, is unaffected. Maybe I should have said that there. Kc is only changed when you change temperature, right? So Q is the only thing that changed in this problem. So if Q is less than Kc, then we remember that this will lead to a forward shift in the equilibrium. To explain that, if you've forgotten, if Q has got too small, Q is now less than K, to reach equilibrium, Q will need to increase, right? Q has decreased, so now Q needs to increase if it's going to come back to equilibrium. How can Q increase? Well, it's a fraction. In order to increase, we would need a larger numerator and a smaller denominator. A larger numerator means more products, and a smaller denominator would mean less reactants. So if we want more products and less reactants, this equilibrium is shifting forwards. Now we memorized this earlier in our unit. When Q is less than K, we get a forward shift. We don't need to go through all of that reasoning again. If we're shifting forward, as we said in the previous explanation, the mass of carbon monoxide decreases. All right, so now a second stress, methanol is being taken out of the vessel. So methanol is withdrawn. We look back up at the balanced equation. This is the methanol, CH3OH, and you're removing it. So looking at a kinetics explanation, we notice that the methanol, CH3OH, is a reactant in the reverse reaction. And the forward reaction is a product. So in the reverse reaction, it was a reactant. So if we decrease the concentration of the methanol, this is going to slow down the reverse reaction, where it was a reactant, but the forward rate is unaffected. Only the direction where it's a reactant is affected. So the forward rate is unaffected. So now we have slowed down the reverse rate. The forward rate didn't change. So if you think of that in terms of arrows, the reverse rate got smaller while the forward rate didn't change. So now the forward rate is larger than the reverse rate. So the reaction is going to shift in the forward direction. Okay? The forward rate is larger than the reverse rate. We shift forward, and we get a decreased. I just realized I'm not showing you this. We get a decrease in the carbon monoxide mass. Okay? So because the methanol was a reactant in the reverse reaction, only the reverse reaction rate is affected. So in the end, we have a faster forward rate, the reaction shifts forwards, and we get less carbon monoxide. Now, in terms of the reaction quotient, let's look back at our expression for Q, and we notice that methanol is in the numerator of Q, and we have just taken some methanol out of the container, so we've decreased the methanol's concentration. So let's think about what that does to Q. So I'll note here that methanol concentration was decreasing, and it's in the numerator of Q. So since the methanol concentration is in the numerator of Q, Q will decrease. When your numerator gets smaller, the fraction also gets smaller. Kc, I didn't say this up above, but Kc is unaffected. The only thing that changes unaffected. The only thing that changes Kc would be changing temperature. So if Q has got smaller, but Kc didn't change, Q is now less than Kc, which leads to a forward shift in the equilibrium, and we get a decreased mass of carbon monoxide. Alright, so notice you can use either one of those explanations, whichever one makes more sense to you, but try to understand both, because on a test I might use one explanation in a question, and you want to be sure you're a little bit familiar with both, but in an open free response question asked to explain, you can choose one method or the other, and choose whichever one you're more comfortable with. Alright, cooling down the vessel. Temperature changes and volume changes, the next stress, these are two of them a little bit more complicated to explain. So let's go back to our kinetics thinking. When you cool down the vessel, you're cooling down the system. We remember from our kinetics unit that temperature is one of the factors that affects rates. And when you cool down the system, that's supposed to slow down the rates. So the first thing I'll say is cooling will slow down both the forward and the reverse rate. Okay. Now what I'm going to say next, we didn't really give a good explanation for. I just asked you to accept this as a fact. The explanation for it is a little bit beyond high school chemistry. So although both rates are going to slow down, when you're cooling, changing temperatures, it would be the same thing if you were heating, the endothermic direction is affected to a greater extent. So if you're cooling, although both rates will decrease, the endothermic direction will decrease to a greater extent in its rate. If you were heating, the endothermic direction would speed up to a greater extent. So the endothermic direction is the direction that gets affected to a greater extent when you change temperature. So the endothermic reaction slows down more. Now if you remember when we wrote our balanced equation earlier, we saw that it was written as an exothermic process. So the forward reaction was exothermic. Then the reverse reaction is the endothermic process. So when we say that the endothermic reaction slows down more, we'll say here that the reverse reaction is endothermic. So it slows down more. So now that the reverse reaction is slowed down more than the forward rate is bigger than the reverse rate. As a result, we get a forward shift, and this is the third time we're seeing that. In a forward shift, the mass of carbon monoxide decreases. All right, so you have to remember this one key fact, that when you're cooling things down, the endothermic reaction rate will decrease more than the exothermic rate. If you were heating things up, the same thing would happen. The endothermic rate would increase more than the exothermic rate. Now, when you're looking at the reaction quotient explanation, we have here for the first time a temperature change. And so the thing I'm going to say first is that changing temperature, Kc changes, but Q, the reaction quotient, is unaffected. Okay? Q is just the ratio of those concentrations that were in the container. So if you're not changing any of those concentrations, Q is going to be unaffected. But Kc will change because we're changing temperature. Kc depends on the temperature. Now this was an exothermic reaction. Again, looking back at the original reaction as written, it was an exothermic reaction that we were given. So there are two possible situations, exothermic or endothermic, and I'm going to sketch this at the top here. And we've memorized these two situations. In an exothermic reaction, Kc versus temperatures, Kc will get smaller at the higher temperatures. In an endothermic reaction, Kc also changes with temperatures, but now Kc's increase with temperature. So you have to remember those two situations. Now in this reaction, we were told it was exothermic. So Kc will decrease when the temperatures are increasing. Therefore, since we're cooling the system down, so cool the system, Kc for an exothermic reaction look at the graph, when the temperature gets smaller, the Kc's get bigger. So Kc for exothermic reactions increase. Okay? The Kc increases for an exothermic reaction. So Kc is getting bigger, but Q did not change. So if Kc gets bigger and Q does not change, Q is going to end up being less than Kc. Right? The Kc got bigger, so Q is less than Kc. That leads to a forward shift. And just like we've seen before, the mass of the carbon monoxide decreases. Okay? So if you're talking temperature and you're discussing reaction quotients, you have to include the appropriate graph in your answer. You don't have to sketch both, but you have to sketch the graph that applies to your reaction. So we were dealing with an exothermic reaction. You have to include that graph with your explanation. Okay? The fourth stress, we are doubling the volume of the container. Doubling the volume, increasing the volume. So the first thing I'll note in both answers is that when you increase the volume, the concentrations of gases will decrease. Okay? Boyle's law from grade 11 chemistry. So increase volume, all of the gas concentrations decrease. Now looking at the balanced equation, okay, there were gases in the forward reaction, and there were also gases in the reverse reaction as reactants. So therefore, both the forward and the reverse rate will decrease. Okay, the concentrations have decreased. That'll make the forward and reverse rates decrease because gases were reactants. If the forward rate did not have a gas reactant, maybe everything there was solid as a reactant, then the forward rate would have been unaffected. But here, both forward and reverse reactions had gas reactants, so therefore both of them will decrease in their rates. Now, both are decreasing, but do they decrease equally? You look at the balanced equation, and we notice that in the forward reaction, the carbon monoxide's coefficient is a 1, and the hydrogen's coefficient is a 2. So if we can sort of think kinetics and rate laws, this is a little bit imprecise, but we can say that the forward reaction rate is third order, 1 plus 2. The reverse reaction rate, the methanol there, the only reactant, has a coefficient of 1. So it's first order. So I'm going to say that here. The forward rate is third order. The reverse rate was first order. So although both rates will decrease, the forward rate has a higher order. So the forward rate will decrease more. Okay? Higher rate. So if it decreases more, then that means we'll have a reverse rate greater than the forward. And this is the first time we're seeing that. When the reverse rate is greater than the forward, we get a reverse shift in the equilibrium, and we will increase the mass of carbon monoxide. Okay? Now, the explanation with the reaction quotient is similar, actually, to the kinetics, in that we're going to be looking at orders again. But this time the orders come from the reaction quotient expression. So I'm going to write that again here. Q was equal to the concentration of methanol over concentration of hydrogen squared and concentration of carbon monoxide. So looking at the expression for Q, we notice that the numerator is first order. Okay, the methanol is raised to the power of 1, while the denominator is third order. The denominator has something squared times something to the power of 1, so that gives me something to the power of 3 overall. So when you decrease all of these concentrations, both your numerator and your denominator will decrease. The denominator, though, will decrease more than the numerator because it's a higher order. When your denominator is smaller, then, that will make your fraction get larger. So therefore, Q will increase. Kc, because we didn't change any temperatures, Kc is unaffected. If Q has gotten bigger while Kc didn't change, then Q is going to be larger than Kc, which leads to a reverse shift, and the same answer that we had earlier is going to give me an increased in the mass of carbon monoxide. All right. We'll do one more here, actually, just for the sake of time. We're going to add a catalyst to the vessel. Now, from a kinetics perspective, we know that catalysts increase the rate of a reaction by changing the mechanism and lowering the activation energy. If you remember on a potential energy diagram, the hill gets smaller with the presence of a catalyst. So the catalyst will increase both the forward rate and the reverse rate. But here's the real key. It increases those rates equally. Okay? When that potential energy diagram's hill drops, the forward reaction rate gets faster and the reverse reaction rate gets faster equally. Okay? Because they change equally, there's going to be no shift in the equilibrium because the two rates will still be equal, right? And so the mass of your carbon monoxide is unaffected. The reaction was already at equilibrium, so the mass of carbon monoxide is unaffected. There was no shift in equilibrium. With Q, it's actually easier to explain. The catalyst does not affect any of the concentrations, so it does not change any concentrations in the flask. So Q is unaffected. The temperature did not change, so Kc is also unaffected. Since Q and Kc were both unaffected, then the Q is still equal to the Kc as it was because the system starts at equilibrium, and therefore there's no shift. With no shift, the mass of carbon monoxide does not change. Okay? Now, the last stress about helium being added, you can actually make a similar argument with that as we just did with the presence of a catalyst, as long as the volume does not change when you add the helium. When you add helium, a noble gas, it doesn't react with anything. Neither the forward nor reverse rates are affected because the helium is not a reactant in either one of those reactions. With neither rate affected, there's no shift in equilibrium. When you look at the reaction quotient expression, helium is not in the expression. The addition of helium won't change any of the concentrations that are there because the volume doesn't change. So therefore, adding helium, Q is going to be unaffected. Since temperature does not change with the addition of helium, Kc is also unaffected, and there will be no shift in the equilibrium. All right, so there's a quick review of Le Chatelier's principle with detailed explanations as you would put on a free response question.